Good morning, Year 10. Can you please pause the video and complete the low stakes quiz? Okay, welcome back, Year 10. The yellow box that you're noticing on this slide denotes that this is something that you must do. I don't need you to ever write down questions from my videos, but you must do anything that is in a yellow box. So if that is questions, you must answer the questions. If that is notes, I'll be telling you to write the notes. So the yellow box just denotes my expectations of you in this video. So going through the answers, you must now mark this in green pen or a different colour pen to what you wrote in. Prokaryotic cells contain no nucleus. Acids have a pH between 1 and 6. The circuit symbol for a cell is that, a voltmeter and an ammeter. If a charge of 100 coulombs flows for 10 seconds, what is the current? So we need to remember the equation that we learned yesterday. Q equals I times T. Now we're being asked to find I, and we need to be able to rearrange this equation to make I the subject. So Q divided by T equals I. Expectation that you should be able to do that. I know quite a few of you are doing that in maths at the moment. So Q is our charge. So we've got 100 divided by 10 seconds, which means that I equals 10 amps. And that is our answer. Okay, onwards with today's lesson then. So we are looking at circuit basics today. We're going to be looking at series and parallel. We're going to be looking at potential difference. We're going to be using an equation to calculate what energy is being transferred by potential difference, and so what actual potential difference is. Now, some of this you will have come across before, certainly series and parallel circuits. I would have expected you to have heard about at Key Stage 3. I would have expected you to have played around with batteries, with bulbs, with wires. And normally that's exactly what we would be doing in the classroom right now. However, we're not able to do that, but I have got some amazing simulators that actually work and don't take half as long to set up. So on we go. So the potential difference. Can we have a subheading of potential difference? It is the energy between the two different points on a circuit. So here is my circuit, here is my cell, and here is my light bulb. And this is the positive end of my battery, and this is the negative end of my battery. Now, we know that electrons are negative, and actually we know that electrons are going to travel around the circuit going from negative going back to positive. However, many years ago, they didn't know that, and they actually did an awful lot of the rules of electricity before they worked out what electrons were. I know that sounds a little bit daft in this day and age when we know what electrons are and how they work, but there are still things that we don't know, and yet we still manage to make things work. So this is what we call electron flow, where it goes from negative to positive. But if you ever hear of conventional current, that is where it is travelling from positive to negative. Okay, so what is actually happening? So we talked yesterday about charge, and charge is where you've got a coulomb of electrons. Now remember, a coulomb of electrons is just a specific number of electrons moving around the cell. And the amount of those electrons moving around the cell will give rise to the current. Remember, we've got our equation, Q equals I times T, because I, which is current, is the amount of charge per second or per unit time. So here, however much charge we have per unit time is what our current is equal to. So effectively, if you think of the current as being the vehicle that is moving around the circuit. Now, potential difference is the energy difference between 2 points. It's got the units of volts. Now, I would have expected you to have heard of volts before now. You'll have certainly talked about voltmeters when you're referring to electricity back in year 8. And you might even remember that voltmeters have to be placed in parallel. What that means is that they stretch from one side of a component to the other side of a component. And so we can, when we're measuring the potential difference of something, we are measuring the energy change from when our electrons, our coulomb of electrons, get to here. We're measuring how much energy they've got, and we're measuring what the difference in energy that they've got when they reach the other side. Because in this bulb, this electrical energy that is currently flowing around the circuit is going to be converted into a different form of energy. In the case of a light bulb, it's going to be converted into a light energy transfer. And also heat energy, so thermal energy. So there's definitely a link here between electricity that we're doing now and the topic that you did before Christmas that was energy. So our charge is flowing around the circuit now. It is our charge is picking up energy from the cell. So the cell here, this stores chemical energy. And it pushes the electrons around. Now, what the actual potential difference is, and I'm going to put this coming off here, here we go. So the potential difference is the energy transferred by the electrons. Okay, so the chemical energy from the cell pushes the electrons around the circuit. You've got to have a cell in order to have that energy there to be pushing them around. Those electrons won't move without some form of energy. They'll move in random directions, but they won't move in a specific direction without some form of energy. Now, as these electrons move around the circuit, they have energy that has come from the cell, and that can be transferred to components in the circuit. And that happens by work being done. So we've got chemical energy, it's being transferred to electrical energy, is being transferred to light and heat energy. So the unit of energy is, of course, joules. And so what 1 volt means is it is 1 joule, per coulomb. So for every coulomb of charge, 1 joule of energy is being given when you have a potential difference of 1 volt. And this is interesting because this is a direct link between potential difference and charge. And so through that, there is then a link between the current and the potential difference. because we can work this out so that 1 coulomb is the equivalent of current times time. And so we've got energy per coulomb. What I'm going to write, I highly suggest that you write on yours. So potential difference is the energy transferred per charge. And I will come back to that. But just before we say that, so we know that charge is measured in coulombs, energy is measured in joules, the potential difference is measured in volts. So the higher the amount of energy is transferred per charge, the higher the potential difference. The lower the energy transferred per charge, the lower the potential difference. And I appreciate I've scribbled on that quite a lot. I don't actually need you to necessarily write anything down other than this little bit over here. And that's why there's no yellow squares on here. Okay, onwards then. Now, I do want you to fill in this. So I want you to write out these 1, 2, 3, 4, 5 sentences. And that shouldn't take you much more than 2-3 minutes. So pause the video and do that, and I'll come back with the answers. So the cell stores chemical energy and pushes the electrons around the circuit. Potential difference is the energy transferred by the electrons. The unit of potential difference is volts, and that's using the symbol V. Electrical work is done by the electrons as they pass through the component, and the unit of energy, joules, and the unit of charge is coulombs. Okay, so I hope you got that right. There it is in type. Make sure that you have highlighted the words, make sure you've corrected them if you need to. I am expecting to see this deliberate practice handed in. Okay, now we are going to go on to look at this equation. So this is the equation that we've just been talking about, although we had it a slightly different way around. I need you to write out this equation. So energy, which is symbolised by a capital E, and this has the units joules. Q is charge, and this has the units of coulombs. V is potential difference, and this has the units of volts. Now, this equation is another equation you're going to be required to rearrange. You're going to be required to make Q and V the subject of that formula. Now, if you do that, either way, you are going to need to put the other symbol onto the other side. So, for instance, if I want to make Q the subject, I divide both sides by V. So, Q will equal E divided by V. And V will equal E divided by Q. You need to be able to do that. You need to learn this equation. You need to be able to rearrange it to form either of those equations, depending on what you're being asked to do. Okay, watch this example. You're going to have a go at on the next page. So, find the energy transferred. So I need to use the equation as it is by a bulb if 355 coulombs of charge flow when connected to a potential difference of 12 volts. So E equals Q times V equals 355 times 12, which equals 4,260 joules. And I must put a unit on there. Okay, so questions for you to have a go at. There's one requiring each rearrangement of the equation, so pause the video and have a go. Okay, welcome back. Hopefully you've had an attempt at these. Now I'm going to go through the answers. Can you make sure that you mark whether you have got them correct or incorrect? So, what is the energy transferred? So I'm using E equals Q times potential difference. I've got 456 coulombs times 120 volts. And so I'm coming out with 54,720 joules. A hairdryer transfers 325 joules of energy when connected to a 9-volt supply. Find the charge that has flowed through it. So this time we're looking for Q. So I rearrange my equation. Q equals E divided by V. So 325 joules divided by 9 equals my charge. 325 divided by 9 is 36.1 coulombs. And finally, an electric heater is plugged into mains at 230 volts and transfers 1,450 joules of energy. How much charge flows? So again, I'm using Q equals E divided by V. So it's the same equation. I thought they were different ones. Never mind. So equals 1,450 divided by 230. We'll come back to that. That is actually mains voltage. 1,450 divided by 230 equals 6.3 coulombs. Okay, hope you were okay doing those sums. They are relatively simple. It's just another equation that we need to add to the memory and we need to make sure we have practiced. Okay, so now we're going to move on and look at series circuits. Now, series circuits, everything is on the same loop of wire. And in parallel circuits, there are multiple loops of wire. Now, I'm going to take you off now and show you, use a website simulator. Yes, please. There we go. Okay, so let's blow this nice up and big. And let's go back down to one battery. So, a nice simple circuit. We've got one cell, we've got one bulb. Okay, and if I put the amp meters and the voltmeters in there, I can see that the battery is giving off, or the battery is supplying 1.5 volts of potential difference around the circuit. Now, what we know that means by our potential difference equals the energy transferred per charge. So every charge going through there is picking up 1.5 joules and carrying it. So every coulomb of electrons is carrying 1.5 joules of electric energy to the light bulb, and there that is taking its 1.5 joules of electric energy and it is converting it into light energy and heat energy. Whether we're getting 1.5 joules of light energy is very unlikely, because that would imply that it would be 100% efficient. Now, we also look at what else we've got in the circuit. Is we've got our amp meters telling us that we've got 0.1 amps. Now, a key thing to notice here, this is a series circuit. We've only got one bulb in it, so it's only possible for it to be a series circuit. And the current, which is being read by the amp meters, is the same. Now, what happens if I add an extra battery? Notice the light gets brighter and everything has doubled. So the potential difference being given off by the battery. So remember that is the energy being transferred to every coulomb of charge has doubled. How much the lamp is taking has doubled. And also the current has doubled. Now, I did say very much a relationship between voltage and current. Now, if I go up to 3 batteries, my bulb is blown. So my bulb is no longer taking any potential difference from the circuit, and the current is 0, and actually the circuit is broken because of the fact that I've put too many batteries in it. But if I go back to 2 batteries to 1 bulb, so I now know that this is a 3-volt bulb. If I supply any more than 3 volts, that's going to cause too much energy to go through that filament wire, and it's going to cause it to overheat and not work. Now, we're really interested now in looking at series circuits and parallel circuits. So, in a series circuit, everything is in one loop of wire. And that's really, really key. So the battery is still there. The battery is still giving energy to the circuit. Now, one battery, let's put the voltmeters back in. One battery is supplying 1.5 joules per coulomb of electrons, so 1.5 volts. Now, notice now, when we had a single bulb, 1.5 volts from the battery was going to 1.5 volts with the bulb. However, we've now got 2 bulbs in the circuit, and the potential difference that is being drawn from the battery has to be shared between the components within that circuit. So because there are 2 bulbs, they share the 1.5 volts that the battery is given out. If I put more batteries in, each bulb gets more potential difference until we've got 6 volts worth of batteries, meaning the lights are burning as brightly as a single bulb was in that circuit. So notice those circuits are now completely comparable. We need twice as many batteries in order to make the bulbs as bright. And again, if I go up another battery, I'll go over the 3 volts that these bulbs can take. The bulb no longer works, and that means that my circuit is broken. So, in a series circuit, the potential difference is shared between the components. So that means whatever the voltage is over the battery, whatever the potential difference is over the battery, will be shared between any components within the circuit. And there is some adjustments I'll make for that tomorrow when we discuss resistance and where that comes in. Current is always going to be the same. At any point in a series circuit, the current will always be the same. So series circuit, potential difference is shared between the components. Current remains the same all the way around the circuit, because bearing in mind that the current is the amount of charge that is being pushed around per unit time. And that is the same because it's one circuit. Now, when we go to 2 bulbs in parallel, and notice here, if we open this switch, this light goes off. If we open this switch, this light goes off. But if I open this switch, which is on the loop between the power source and the bulbs, both bulbs go off. So, and this is how the lighting in your house works to a larger extent. The fact that you effectively have lots of parallel circuits that you have switches on. So I can switch the light off in my kitchen and leave the light on in my living room, or I can turn them both off, or I can have them both on, or I can have them the other way around. So I turn the light in the living room off and leave the kitchen light on. Now, volts or potential difference here measured by our voltmeter is very similar. Whatever the potential difference across the batteries is, each component on each loop will get the same amount. So each loop is taking the same amount of energy out of the battery. And because they're on different loops, they don't have to share this time. Again, if I increase the number of batteries, in fact, if I increase the number of batteries, I cause issues to my bulbs. If I decrease the number of batteries, the potential difference decreases. I won't add any more bulbs in. Now, so in a parallel circuit, each loop is treated as an individual series circuit. So here is one loop going round here, round here, round here, and back to the battery. And then the second one round here, down right to the bottom, round here, and back up to the battery. And that does have some implications for current, because where we talked about current before was always the same on that one loop. Now we've effectively got two loops. So what happens with our current is on each loop, the current is the same. So hence on these two wires, where actually they've got exactly the same components in each loop, the current is the same. But where the two loops join up together, and if you almost think about these wires overlapping each other, this is where we've got a double current. So our current here is twice as much as it is on the individual parts of the circuit. So where the circuit is split into parallel, where it's all met back up, the voltage is doubled. Okay, so I've got a deliberate practice that I'd like you to have a go at. So this is a series circuit. Ammeter 1 over here is showing 1 amp. I want you to tell me what will A1 show and A2. So this is a series circuit. If you need to rewind the video and go back and watch the explanation I did on series circuits again, feel free to do so. And the series circuit has got two components, two bulbs in. It's got a potential difference being given off by the battery of 6 volts. And I want you to tell me what will the potential difference of voltmeter 1 and voltmeter 2 show. So can you write those answers down? This is the final deliberate practice for this lesson. Okay, so going through our answers. Well, the potential difference for the circuit, or available for the circuit, is 6 volts. Now that's shared across two components. So that means that each of these voltmeters will be reading 3 volts, because the 6 volts will be shared across the two voltmeters. The current in a series circuit is the same everywhere you go. So ammeter 1 will show 1 amp, and ammeter 2 will also show 1 amp. There's a lot of thinking involved in that lesson, ladies and gents. I am going to post this, but I'm also going to put a link to what I think is quite a helpful online resource, the one I was using for you to have a little play with. Make sure you've done the 3 sections of deliberate practice. Make sure you've marked your work. It wasn't a huge amount that I was asking to be written down, but I am aware that that was a difficult lesson. If you've got any questions, do please ask them. I am on the chat. Thank you very much, Year 10. Have a lovely day.